What is a climate model? Or more generally, what is a model? A model is a representation of reality, and such a representation must always be simplified. It can never represent the whole reality. Take a city map. A city map is a model, a representation of the real city. A city map must include the essential attributes. For example, it needs street names, it may need house numbers, or maybe not. If you're traveling by car, you need one-way traffic to be indicated. However, you do not need trees to be represented. Thus, a good model includes the essential attributes for the required purpose. And the same is true for a climate model. A good climate model represents the essential variables, the essential attributes of climate. Such a model is indispensable when you want to represent conflicting effects in climate. Let me clarify this with an example from my time at university. The photo shows how I looked at that time. It was the first time I heard of a climate issue caused by carbon dioxide during a lecture. I told fellow students about this, and one of them replied, "But that's really no problem. I've heard that if it gets warmer, the air will get more humid, then more water vapor is in the air, there are more clouds, the clouds have a cooling effect and thus dampen the effects of CO2. The climate issue is therefore no real problem." I had no reply to this objection at that time. Nowadays I know that reality is much more complicated due to conflicting effects. It is indeed true that some clouds will appear more frequently. However, other clouds will appear less frequently. And the question is, what is the overall effect of the change in cloud cover? And we need a climate model that represents all the major attributes of climate as realistically as possible to represent this overall effect. Let's just look at essential elements and processes in climate. These are illustrated in this graphic. We have the atmosphere with clouds, we have the ocean, we have the sea ice, we have the land surface, and then we have other major processes that affect climate. For example, solar radiation and volcanoes. We want to represent all these processes, all these attributes in a model. How do we do that? First of all, we consider the basic laws of physics: the conservation of mass, the conservation of energy, the conservation of momentum, that is Newton's laws of motion. These basic laws are represented mathematically, that is, expressed as equations which are then solved. What does this look like in practice? This is illustrated in the next graphic. We write separate equations for the essential elements of the climate system. For the atmosphere, for the oceans, including the sea ice, equations for the terrestrial biosphere, equations for ocean biogeochemistry, and here mainly for the ocean carbon cycle. Then we need to couple these different subsystems. For example, the atmosphere and the oceans, because there is an exchange between them. In the case of the atmosphere and the oceans, they exchange water, hence mass. Evaporation means that water is taken out of the ocean and deposited in the atmosphere. Precipitation means that water is taken out of the atmosphere and deposited in the ocean or on land. All these processes, including the exchanges, are expressed mathematically as equations, and then we solve these equations on the largest computers available to us.